Welcome back to episode 4 in our Representing Data series. Hopefully you've seen the rest of the videos. This one's all about sound. What improves the quality of sound is the key question. Well, you've got to find out all about that. Know that sound is analog, continuous, and we have to convert that to a digital form for a computer. We know that the sound waves are sampled to get you that digital version. You're going to learn about the terms sampling rate and sample resolution. And you're also going to be able to work out file sizes for sounds using those two terms, sample rate and sample resolution. Well, let's go and see how we do all that. When we record sound, us humans, we hear it continuously, all the time. We've got very good hearing. We've had hundreds of thousands of years of evolution to do that. A computer can't do that. It just can't sample everything all the time because it just wouldn't have enough space to store it all. So what it must do is it must sample it. It must listen at certain set times. The more you sample, the more you'll listen to that sound, the more accurate it should be. And what you're doing is you're measuring the amplitude, the ups and downs of where it is on that wave. You measure sampling in hertz, and it's known as the sample rate. How often you sample is the sampling rate. 1 hertz is 1 sample every second. CD quality, so very close to what we'd hear if we were actually right there listening to the band or the music, is sampled at 44,100 hertz. So key term, sampling is a sound measurement taken at a given point in a sound file. Let's look at this graphically. Here is a sound wave. Along the bottom you've got as time is passing, and up the top here along the side is the amplitude. So if we think that we recorded at 1 second, here's the time sample down here, 1, the amplitude at that point was 5, 6, 7, 7.5-ish. So 7.5. At time interval 2, it was 1, 2, 3. It was 3. And that's what it does. It just records when the time sample was taken, what the amplitude was. And it converts those into binary and it stores it in a sound file. When you play back that sound, the binary values are then used to recreate the analog sound. What do we hear analog sound in? Headphones, speakers, something like that, which will hit our eardrums, make them vibrate, and then we'll record what that sound is with our brain. And those samples you could use to recreate a sound wave. Think about what we did that run. Remember we had time sample 1 was at 7.5, 2 was at 3, and so on. And then you can then join the dots to get you a sound wave. But if we overlay the original sound with this one that we've recreated, there's a big difference. Starts off well enough, but then it starts to lose. They start to not match anymore. So that sound's not going to be exactly the same as the original, because it's only using the samples to recreate that. And the time that that sound was being played between those samples, it has no idea about. It's got to fill in the blanks. I mean, look at the end of the sound wave. Really lost it there from time interval 6 onwards. I mean, there's really, it's just shown a general decline, but there's been too much going on. It's not sampled it enough. It just sees it going slightly down, doesn't know there was a number of ups and downs in between that. That's not going to be accurate. So hopefully now what you do is you understand that sound is analog, but it has to be converted to digital by using samples to create a digitized version of that. You should have a clue now about sample rate and sampling resolution, which we'll talk about in a minute, affects the output of sound. Sampling rate at least. You saw that it was not accurate at the end of that last sound wave. Wasn't sampling rate, wasn't doing it enough. Sampling rate wasn't quick enough. The more that you sample, the frequency at which you sample, that will affect the quality. If you're listening an awful lot of times per second, you can match the sound a lot more accurately. That's the sampling rate. So if you look at that previous example, the sampling rate wasn't very good, wasn't enough, and we lost it there at the end. How we've improved that? Well, what we should have really done was increase the sample rate, listen an awful lot more times more to get the amplitude more accurately to what it was at that point in time. Imagine we'd doubled the number of samples. That would have given us a much better representation of the original wave. So remember, sampling rate, that's the frequency at which we take the samples. And just to labour that point, the more samples we take, the more accurate reflection it will be of the original. That's why at CDs you do it 44,100 times per second, because you want that output to be as close to the original sound as possible. Telephone conversations, though, they're done at 8,000. Why do you think that? Why do you think that a telephone conversation is sampled less than a CD? Well, first of all, the voice doesn't have to be as accurate, doesn't have to be as precise as a piece of music. Also, when you're sending your telephone conversation, you are sending data down a line. You might want to reduce the amount of data you're sending, so you might want to listen to it a little bit less. But that's the trade-off. If we listen a lot more and our sampling rate improves and we get a more accurate version of the voice, well, that's going to increase the amount of data that's going to be sent. It's going to cause a larger file size, which means we need a bigger amount of bandwidth and network capabilities to handle all of that. And why is that? Well, simply because there's more samples. You're doing more samples. Instead of doing 8,000 a second, you're doing 44,000 a second. So that's quite a lot of an increase to send as information. So the file size is going to get bigger and bigger. There's also something else, though, called sample resolution. A bit like color depth. If you think back to the previous lesson, the color depth was the number of bits that we assigned to record the amount of colors. Well, the sample resolution is the number of bits that we assigned to record that sound. The more bits you give to record that particular sound at that particular point in time, the more accurate it will be to the real world equivalent. Very much like color depth, if you use 2 bits, that will give you 4 values you could measure to represent that sound you heard at that point in time. 8 bits would give you 256 values to measure. So what's sample resolution? How much data we need to store one sample at that one point in time when you've sampled, your sample resolution will be used. CDs, 16 bits to represent each sound it hears. Trade-off being is, the more sample resolution, the higher the sample resolution you're using, yes, the more values you can be measured at that point in time, but the file size is going to go up. Calculation-wise, the file size needed to store a sound clip is this particular formula. Length in seconds multiplied by the number of samples you're taking per second multiplied by the sample resolution. That will give you an answer in bits. So very much like images, where it was number of pixels multiplied by color depth to give you the answer in bits. This one, where you have the number of samples per second multiplied by the sample resolution multiplied by how long that clip is, will give the answer in bits. You'll need to divide by 8 to get to bytes. Here's an example. 10 seconds long, sampling rate of 100, sample resolution of 4 bits. That will be then 10 for the length, multiplied by 100 for the number of samples taken in that second, 100 Hertz, multiplied by 4, which is the sample resolution, will get you 4,000 bits, which is, divided by 8, 500 bytes. Here's one for you. Pause it, work it out. 8 seconds long, multiplied by 50 samples that second, multiplied by 2, will get you your answer in bits, then divide it by 8 to get your answer in bytes, and there's your answer right there. Here's some more questions for you to try. Pause the video, don't use any calculators. Remember, if you have to give the answer in bytes and you can see a calculation as you're multiplying them together and you can divide by 8 simply at that point, do it. So for example, if you're doing 8 times something or other and you know you have to divide by 8 at the end, just divide that 8 by 8 at that point, so it's now 1 times something to make your calculation simpler. Pause the video, have a go. Welcome back. Okay, let's give you the answers then. So question number 1, 5-second clip, sampling rate of 2000, sample resolution of bits. It wants all the answers in bytes, so we have to divide by 8 at some point. So 5 seconds multiplied by 2000 multiplied by 4 divided by 8 gets you 5,000. Don't know how you'd work that out. Me personally, the 4 divided by 8 gets you half, doesn't it? 0.5. That's what I would have done. So then I could have multiplied the 2000 by 0.5 to get me 1000. So 5 times 1000 is 5000 bytes. However you want to do your maths, doesn't matter. But just remember you divide by 8 at the end. Question number 2. 20 seconds long, multiplied by sampling rate of 100 and an 8-bit sample resolution. Great. We know we have to divide by 8 at some point, so let's just do that now. Those 8 bits divided by 8, so it's just 20 times 100 times 8 divided by 8, which is 1. And that'll get you 2000 bytes. Next one, I've got K here. So remember about kilobytes, that was 1000 bytes. Kilohertz is 1000 hertz. If you saw megahertz, that'd be 1,000 hertz. So this is going to be 2 times 1000 hertz. This is 2000 hertz. So 2000 samples. Resolution's 8 bits. 4 second long. 4 times 2000 times 8. And then divide that by 8. That'll get you 8000 bytes. This last question a little bit more trickier because it's going to try and get you to work out how long it is. So you know that the answer itself is going to be 40 kilobytes, which is 40,000 bytes, and then multiply that by 8 to get yourself bits. But use X or exclamation mark or question mark to work out what it is. You know that 40,000 bytes is going to be whatever the length is, we don't know, multiplied by the number of samples, which is 20,000, multiplied by the resolution, which is 8, and then that calculation itself would have been divided by 8 at some point to get you into bytes. So simplify that a little bit more. We know that something times 20,000 equals 40,000. So, either divide the 40,000 by 20,000 or just do a little bit of mental maths. It's going to be 2. 2 times 20,000 is 40,000. So that's how you get that. That's quite a hard one. That's really it for sound. You need to go to Edmodo, go to the quiz, representing data, sound, have a go at that. Recap. You were able to describe how we represent sound and sampling rates and sample resolution, and also calculate the sound files themselves. We'll see you in the next episode.